Okay, so the plan for today is to cover improper integrals. Oh, I didn't quite get these up this morning, but those should be posted this afternoon, and I will send out a Blackboard announcement. Um, so today's plan, improper integrals at the end of chapter 7. And two thoughts for today. One quote of the day. A lot of you are going into maybe engineering or physics, chemistry, one of the like kind of hard sciences, so to speak, the sciences that are based on experiment. Um, and so I think this quote is one to always kind of keep in the back of our mind. One physical test is worth 1,000 expert opinions. It doesn't matter how beautiful or elegant your theory is, if it disagrees with physical reality, with experiment, and not just, disagrees a little bit with one experiment, but systematically disagrees with experiment to the point where the two are clearly saying different things. Um, it doesn't matter how nice your theory is. It doesn't matter how smart the person is saying it or how many accolades they have or whether they're a Nobel laureate or the guy in the corner. Doesn't matter if it disagrees with experiment. It's you know, the experiment trumps the opinion. So it's invalid in some sense. Now, of course, all of the normal caveats to that, like one experiment versus a theory that's been widely regarded for centuries, and widely tested is different. So we're not saying if you do one experiment and get a wonky result. And of course, we're also not saying that, just forget about Newton's laws, never teach them anymore because we know that relativity is a bit more accurate or quantum mechanics is a bit more accurate. No, things have their place, but uh, as a quote, something to keep in mind that the ultimate arbiter is physical experiment with physical reality in the hard sciences. You can have a really pretty theory. It can be a really cool idea. Does it agree with experiment? Um, and kind of related to that idea, uh, I'm on a committee with our resident philosophy professor, Professor Drew Van Land. He is mainly centered out of Allegheny campus. This coming fall, he is starting up a new philosophy course. So right now, I think we offer like philosophy 101 or something like intro to philosophy. And then I think it's 105 is logic. And those are really the only two philosophy courses we have. So he's trying to kind of flesh out our philosophy offerings a bit. And he's come up with a new course offering for this coming fall. The schedule is not published yet, the fall schedule in general for the college. So all the details are, not set yet, of course. And with this being a new course, he's going to, I'm sure, take some time to develop it and decide when to set the days and times, what modality would work best, all of that. But just kind of putting this on your radar, this Philosophy 206, Philosophy of Science, he's looking at offering in the fall. So I wanted to mention it because I think philosophy dovetails nicely with STEM in a lot of areas, but particularly things like philosophy of science or epistemology, like the philosophy of knowledge. What does it mean to know something or to kind of be convinced that something is true? Um, and I think philosophy of science, he's going to get into things like what differentiates science from pseudoscience? What are the aspects that we might look for in the evidence or the presentation of the argument uh, to delineate between one versus the other, or the misinformation or that kind of thing, right? I mean, these days we have the sometimes overwhelming task of curating information. We ask a question to Google and we get 50 different, seemingly conflicting responses. And I have to choose a couple of these to weight more heavily than the others. On what basis should I make that choice? So I think that might be uh, a flavor a little bit of what he might get into in philosophy of science. So, once the fall semester course schedule is published and out there, I think that's maybe in month or month and a half or so that'll be available. I'll probably, plug it again just to remind you, but just throwing this on your radar if that's something you'd be interested in. Um, so you're probably beside his current philosophy students, you're probably the first students to know about this course that he's offering. So if that's something you find interesting, something you'd like to pursue, um, keep an eye out for that. And like I said, when fall registration comes around, I'll probably plug it again if I remember at that point. A month from now seems like forever in the semester calendar. Okay, so that was just a couple quick thoughts for the beginning of class, and moving on to 7.8 improper integrals. So what are improper integrals? Well, long story short, they're integrals that have an infinity somewhere. We might be looking at integrals like this, for instance. Let me zoom this in a little bit. So a lot of detail in these integrals. Something like integral 1 to infinity of 2 to the minus x dx. What does that infinity at the top of the integrand even mean? Or like a doubly infinite integral this way. Or infinities that might not be so apparent at first, integral 0 to 1 of some function that looks like just a normal integral, but we notice that this is a kind of 1 over x type deal. And as we approach 0 from above, that's going to shoot off vertically to infinity. So these are kind of horizontally going to infinity, and this one is kind of vertically going to infinity. And our inclination might be just to say, well, okay, I guess these are all just infinity, right? Is it just like, is it like equals infinity, but not so fast. Let's take just kind of a hand-wavy schematic look at what something like this might look like. Okay, so I have this idea of 2 to the minus x. This basically looks like e to the minus x. And it picks up at x equals 1 and exponential decay to 0. And I know that this integral represents the area under this curve. And we say, oh, well, I mean, it's an infinitely long, I don't want to say strip, that has a very specific meaning, but an infinitely long chunk of material, it's got to have infinite area, right? Well, let's think for a minute about this. This is kind of like adding up a bunch of 1 over 2 to the powers, right? It's kind of a little bit like 1/2 plus 1/4 plus 1/8, 1/16, and so on. I mean, not exactly, but kind of morally speaking, it has a similar feel. And you might have seen this example before and know where I'm going with this. If you take a circle, this circle is 1 unit. It has area 1 unit. I could split this circle in half, color in half the area. And then what I have remaining is a half. I could split that remaining bit in half, color in half of that area. Well, that's half of a half, that's 1/4. I could split what remains, the 1/4, in half, color in that bit, that's 1/8 that I just colored in. I colored in 1/8, I have 1/8 left over, I can split that in half. I color in 1/16, I have 1/16 left over, split that in half, color in 1/32, I have 1/32 left over. You can see that I can do this forever. I'll always be coloring in an amount, and I'll have that amount left over, and I split in half, and I can just repeat the process forever. I can add up infinitely many positive things forever. But clearly, at the very least, we can argue that this is never going to get above 1, but it seems like it ought to be equal to 1. And indeed it is. Later on in the course, when we talk about infinite series, we will see this. But so the point is that I can add up kind of infinitely many positive terms, or maybe infinitely many positive chunks of area, and possibly, not all the time certainly, but possibly end up with a finite sum, a finite result, or a finite total area. Now, importantly, I mean, this is just kind of an analogy, so I'm not saying that this integral ought to be equal to 1 or anything like that. It's not going to be. But the point is simply that we can't just look at, oh, let me close my emails. There we go. Otherwise it'll be dinging all class period. We can't just look at this and immediately chuck in equals infinity or something on the end and be done with it. It's a little more nuanced than that. Now, pretty clearly, if I was to add 1 plus 1 plus 1 plus 1 infinitely many times, I think we can all agree that will go to infinity if I just add the number 1 to itself a ton of times. So what's really happening here? Well, number one, these terms are getting small, but particularly they're getting small very fast. They're getting small exponentially fast. And that's pretty fast. That's faster than like getting small like 1 over x or 1 over x squared, like 1 over e to the x is getting small pretty fast. So these terms are getting small enough, fast enough, that I can add up infinitely many of them and get a non-infinite sum. And similarly, in fact, these areas, these little chunks of area are indeed, I'm just telling you this now, we haven't proven this, but they are indeed getting small enough, fast enough that we can add them up. We can perform this integral and get a real number out, not an infinity or anything like that. We have an example like this, integral minus infinity to infinity of x times e to the x squared dx. This is a doubly infinite integral. And this one is pretty obviously infinite. When x is 0, we are at 0 here. Well, I guess I shouldn't be so flippant. I'm being a little bit careless here, aren't I? On the right-hand side, we have this kind of behavior. On the left-hand side, we actually have this kind of behavior. If this was x squared e to the x squared, which was what I had in my mind at the beginning, this would be an obvious infinite integral because we're adding up essentially chunks of area or terms that are positive all the time and getting bigger and bigger as the further we go out in both directions. If I had something that was like integral of, say, e to the negative x squared, something like this, that's the famous bell curve, that actually does come out to be a real number. If I had this particular one, x e to the x squared, it looks like this. It's an odd function because of that x to the first power. I was jumping ahead of myself. And interestingly, I noticed that like if I integrate from say negative a to positive a, I get a positive area here. And let's make this in red maybe. A negative area here, and the two are the same area. If I integrate this function from -1 to +1, it's 0. Or integral from -2 to +2 is 0. Integral from negative a to a of x e to the x squared dx is 0. Is this 0 then? Well, we'll see in a little bit. Or if I look at something like this, here I'm integrating 0 to 1. I have nice real number bounds. I'm not looking at a horizontally infinitely long area. When x is 1, I have 1 over root 1, or just at height 1 here. But this function has a vertical asymptote at 0. It's kind of like infinitely tall. If I tilt my head 90 degrees, can I do a similar kind of thing? This isn't quite how integration works, of course, not Riemannian integration, but could I do a similar thing and argue, I mean, of course, this area contributes too, but that's just one unit of area. Really, the question is, what is happening to something like these pieces? It has a little bit of the feel of the integral from up above, the 2 to the minus x, just kind of flip 90 degrees. But we can see that the technical details are going to be different because Riemannian integration makes us integrate this way. something that we'll see come up over and over in Calc 2, and we've already seen a bit in Calc 1, is as soon as we start throwing around infinities, or for that matter in Calc 1 divided by zeros, right? A limit as h goes to 0 of stuff over h. As soon as we start throwing around things that look like infinity, we have to be very, very careful. We have to stick close to our definitions. And we don't want to be too flippant with how we analyze these situations or interpret them. I don't want to just say this equals 0 because it would equal 0 if the plus and minus infinity were some real number, but they're not real numbers, right? I don't want to just say this is infinity because I'm adding up a whole bunch of, or infinitely many positive things. Well, sometimes infinitely many positive things add up to something that's not infinity. Um, I don't want to say this is infinite or doesn't make any sense or something because the 0, this endpoint, is a horizontal or a vertical asymptote. Maybe it does, maybe it doesn't. I'm not really sure yet. The other thing I want to point out is being so definition heavy. Well, anytime that we're talking about, whoops, whether it's infinite series or improper integrals, there are going to be some folks in some areas, some fields of study, who choose to work under different definitions. Their definitions aren't more right or more wrong or something than the definitions we're going to work with. We're working with the standard definitions that are going to be in essentially any calculus textbook that you pick up and look at. These are the definitions that are used. But if somebody in physics working in quantum mechanics says, hey, actually, if I look at this a different way, this is a better model, it's a better mathematical structure for me to use for my thing that I'm studying or thing that I'm trying to use math for, fair enough, they can do that. There are a lot of situations where, if you add 1 and 1, like most people are going to say 1 plus 1 equals 2. There aren't a lot of situations where 1 plus 1 equals 12 is a very useful model. Once you start throwing around these infinities, we end up with a lot more nuance and a lot more subtlety in the way that we can maybe view things or interpret things that might be better here or worse there. So the definitions we're going to work under, if there are some famous like YouTube videos from legitimate channels like Numberphile and those kind of channels that are done by legitimate, PhD level professors at research universities that claim absurd things. But if you look very carefully at those videos, sometimes they're, a lot of times they have clickbaity titles. But if you look very carefully at those videos, you'll realize, oh, wait, they're using a different structure than what we're using. So you have to be very careful and you have to stick very closely to our definitions. And if you look up extra resources, you have to be very careful about what resources you're using. Make sure that they're resources that are intended for, Calc 1 through 3 level students and not for this quantum mechanics course or that relativity course or something like that. Okay, so all of those caveats aside, I feel like sometimes feel like I'm a lawyer when I'm teaching anything with infinities in it. We have, more caveats than content maybe, but all those caveats aside, we have our first definition. Convergence of an improper integral. And this is an improper integral of the type that has an infinite domain of integration. In other words, one of these first two integrals, but not the third integral. The third integral has a finite domain of integration, but an infinite vertical asymptote, a point of discontinuity. Here's our definition. We're interested in this integral, the integral a to infinity f of x dx. That's the structure we're interested in. So it's kind of like this one up here, integral 1 to infinity 2 to the minus x dx. If we see a structure like this, what do we mean by that? Well, here's the definition. If integral a to t, f of x dx exists for all t bigger than or equal to a. So we replace the infinity with basically a dummy variable t. We just stick that t in there. instead of the infinity, if that integral that is now a nice integral over a finite domain, a to t, for t bigger than or equal to a, if that integral exists for all t is bigger than or equal to a, then we define the improper integral, the integral with the infinite domain of integration, as the limit as t goes to infinity of integral a to t f of x dx. So if you thought you were done with limits after, that first chapter in Calc 1, well, sorry, here they come back again. So we do integral a to t f of x dx. X is the variable of integration, so it goes away when we do the definite integral. When we do the integration, we'll be left with something that has a's and t's in it. A we're considering to be a constant, and t the variable. So we take this thing here, which overall is a function of t. We compute what it is, and then we take the limit as t goes to infinity. That's how we define this improper integral, provided that the limit exists and is finite. We have a pretty similar analogous definition for integral negative infinity to b, f of x dx. That's going to be limit as t goes to negative infinity, integral t to b f of x dx, again, provided the limit exists and is finite. And then what about a doubly infinite integral? What about an integral where the domain is the whole real line? We go to negative infinity and all the way to positive infinity. Be really careful. We might be tempted here to say this is the integral, this integral is the limit as a goes to infinity of the integral of negative, or sorry, we might be tempted to say its limit as t goes to infinity. It wouldn't be, the end of the world if I said a instead, but to stay consistent. We might be tempted to say, to interpret this as the integral as t goes to infinity of the integral of negative t to t f of x dx. But that's not what the definition says. The definition says, I pick a real number c, I break the integral with that real number. I integrate from negative infinity to c, and then from c to infinity, and add those two together. This integral only exists and is equal to these if both limits exist and are finite. We have an A-type limit and a B-type limit that both have to exist and be finite. Those are very different statements. So be careful about that. A little bit of terminology. In the above cases where the limits exist and are finite, we call the improper integral convergent. So we say it converges to whatever the value of the limit is or the value of the sum of the limits is. And otherwise, if either the limit doesn't exist, if it's like limit of sine x as x goes to infinity, or if the limit exists but is finite, if it's like limit of x as x goes to infinity, then we call it divergent. And we say it doesn't have a well-defined value. It doesn't make sense to say this integral equals this number for any real number. So we would just say this integral is divergent and leave it at that. But if the integral is convergent, then the value is given by the appropriate limit. So let's take a look at integral 1 to infinity of 2 to the minus x dx. I notice that this is an A-type integral a to infinity. So here I need to evaluate integral 1 to t f of x dx, 2 to the negative x dx. I'm going to figure out what this is, and then I'm going to ask what happens as t goes to infinity. So that's the overall strategy. Well, I see that this is integral 1 to t of what, e to the power negative log 2 x dx. If I do that right, that's e to the log 2 would be 2, and then that's 2 to the negative x, so that looks good. So this is just writing 2 as e to the log 2, or 2 to the minus x as e to the log 2 to the minus x power. If I integrate e to the stuff, I get e to the stuff back. If I were to differentiate, I would pop out an extra factor of negative log 2, so I need a negative 1 over log 2 in front to fix that. And now I need to evaluate from x equals 1 to t. Or what is this? Negative 1 over log 2. E to the negative log 2 t is 2 to the negative t minus e to the negative log 2 times 1 is 2 to the negative 1 minus 1/2. Okay, so what do I see? So this was all just kind of scratch work. To evaluate this integral, I need to evaluate limit t goes to infinity, integral 1 to t, 2 to the minus x dx. Well, this is limit t goes to infinity of negative 1 over log 2, 2 to the minus t minus 1/2, and another square brackets. And this, well, as t goes to infinity, 2 to the minus t goes to 0. That's 1 over 2 to the t, that goes to 0. Nothing else has a t in it. So the negatives cancel and I get 1 over 2 log 2. This limit does exist, and it's finite. And because of that, I can put an equal sign here and say that the value of this integral, well, I can say this integral is convergent, and its value is 1 over 2 log 2. Now, if I got to the end here and got a limit that didn't exist or that wasn't finite, then I would just go back and say this integral is divergent. It's not all that bad. I mean, it's somewhat bad form and somewhat bad notation, but it's not all that bad just to write equals this limit and then later on just, fix it if you need to. But I was trying to be kind of careful with the logic here. We really need to evaluate the limit, show that it is, that it exists and is finite before we claim that the value of this integral is equal to the value of this limit. So what about this example? Integral negative infinity to infinity of 1 over 1 plus x squared dx. Again, we might be tempted to do something like take a look at integral negative t to t, 1 over x squared, 1 over 1 plus x squared dx, and ask what happens as t goes to infinity. But this isn't actually what our definition says. It says we have to break this into 2 separate integrals. We can choose the point that we break it, so let's choose one that's convenient, but we do have to break it into 2 separate integrals, evaluate each independently. So I need to, maybe I'll split it at 0. That seems pretty reasonable. I need to evaluate integral 0 to infinity, 1 over 1 plus x squared dx, and integral negative infinity to 0 of the same. I'll leave this one as an exercise. But for integral 0 to infinity, here I need to look at integral 0 to t, 1 over 1 plus x squared dx. Or this is arctan of x. The derivative of arctan x is 1 over 1 plus x squared, evaluated from 0 to t. or this is arctan t minus arctan 0. And I know that tan of 0 is 0. Tan theta is sine theta over cos theta, so tan 0 is 0, so arctan 0 is 0. So this is just arctan t. So my integral from 0 to infinity, 1 over 1 plus x squared dx gives me arctan t. Or I'm sorry, the integral from 0 to t of that gives me arctan t. And then to get my integral 0 to infinity, I ask what happens as t goes to infinity here. I see that limit t goes to infinity of integral 0 to t, 1 over 1 plus x squared dx is limit t goes to infinity of arctan t. But that goes to what? So I know that I have tan theta and theta. Uh, so so I get a vertical asymptote here when cosine 0, where that's at pi over 2, right? What about arctan? And I flip everything about the line, well, the 45-degree line, the line, I guess, y equals theta in this case. I see my horizontal asymptote here on the right is going to be at pi over 2. So this limit pi over 2 does exist and is finite. And I can now claim that this is the value of that integral. Now, as a side note, this will also be equal to pi over 2. And so this integral will end up being the sum of these two because both of these integrals exist and are finite. So the overall value of this integral is pi. Any questions on this one?
I I,
Um,
I have a
yeah.
question.
Mhm.
Uh, like say you have a function. I see like with the integral from infinity to negative infinity, you're breaking it and picking a real number.
Mhm.
What if like you have something like sine of 1 over x and it like oscillates towards 0?
Yeah, yeah. Yeah, so that's a good question is what if I had something like integral negative infinity to infinity sine 1 over x dx? We are leaning on the fact that this is continuous on the whole real line, or on the whole domain of integration. Same thing with this one. So I have a continuous integrand over this domain. This is discontinuous at 0. Uh, so it's not so much kind of the infinities aren't so much the problem here, right? If I looked at integral 1 to infinity sine 1 over x dx, um, if I put in a very a very big value for x here, 1 over big value is close to 0, and and sine of a number close to 0. Geez, sorry. Sine sine of an input close to zero is going to be close to zero. So, as we head out towards infinity, this is going to look kind of like 1 over x. That can cause some problems. Um, but the really big question is, what does even this look like? Um, and I think this would, so so we definitely talk about limits of, say, sine 1 over x near zero, or limits of x sine 1 over x near zero with a squeeze theorem. We talk about those in Calc 1. I think this is probably beyond the scope of this course. But yeah, so I think an integral like this would take quite a bit of care. Something like this we could probably handle. We might need to be a little careful with some details, or maybe extend some definitions a little bit, but we would basically see that this is going to kind of look like integral 1 to infinity of 1 over x dx, at least kind of morally speaking. And it's basically going to turn out that this is divergent.
What if it
But
was
oh yeah,
sine to the x instead of sine of 1 over x,
what if
so
it
that
was
it
what?
oscillated? So, instead
Oh,
of
oh,
sine of 1 over x, what if you did sine of x so that it oscillates forever?
oh, okay, yeah. So if it was just sine of x, so that's one that we can do. Integral, let's even say 0 to infinity sine of x dx. Well, not equals, but let's investigate integral 0 to t sine x dx. And that's going to be what? Negative cos x from 0 to t. That is -1 times cos t minus 1. And what happens to this as t goes to infinity? Well, this limit doesn't exist. Cosine just keeps oscillating. Does this make sense with our area? If I look at sine x, it looks like this. And I can kind of clearly see that if I set t to be here, here's 0, then my area is positive. If I set t to be here, I have a negative counteracting. So now my area is 0. So I have a positive area, a 0 area, a positive area, a 0 area. So I see that as I'm going out, I can always find a place where my area is going to be positive, and a little bit later, a place where my area is going to be 0, and then positive again, and then 0. So this area is never really settling down to a certain number. It always just keeps oscillating between, I think it'll be, let's see, I think it's positive 2. I, I think this area is 2 there. It's always going to oscillate between like 0 and 2 and just keep bouncing between that. Oh yeah, because cos of t minus 1 times -1 is going to be between 0 and 2. Yeah, so it does make sense kind of geometrically when we look at the picture, and we see through the definition that this limit is not going to exist, because limit t goes to infinity cos t just doesn't exist. It never settles down to a value, or we can never set an epsilon, an output measure. If we set an output measure below 1 unit, we're always going to be outside of the corridor limit plus or minus epsilon at some point in the next 2 pi units of input. So um, I hope that makes sense. So if this makes sense, this kind of Calc 1 limit, um, then the algebra should make sense, and I hope the geometry also makes sense. Yeah,
Gotcha.
so oscillating like this, we can handle oscillating like this because the real challenge here is that we have faster and faster oscillations as we get closer and closer to zero. So something like this, I don't think we can really handle in just kind of basic calculus, even if we extended definitions a little bit or anything like that. So here's an example that can maybe pretty easily trick us. So true or false? Because of symmetry, because we have an odd function in the integral, is the integrand, integrated over a symmetric interval, then this integral has to be zero. We have a theorem that basically says integrating odd functions over symmetric intervals gives you zero. And the idea is that, well, geometrically, your odd function is rotationally symmetric about the origin. So I have the same magnitude of area here as I have here, but this is positive and this is negative. And so my areas cancel. That's kind of the idea. And yeah, this is a theorem that I prove in Calc 1, and also the kind of other related theorem is that the integral of an even function over a symmetric interval is twice the integral of that function from 0 to one of the endpoints. So can we claim this here? Can we extend this theorem to the case where we have infinitely long domains? Well, let's take a look at this. Integral negative infinity to infinity x cubed dx equals 0. What does x cubed look like? It looks like this and like that. And again, we might say, if I integrate from, well, let's say negative t to t, I have positive over here, negative over there. These areas cancel out. And I might feel pretty confident claiming this. But again, is this what our definition says? Remember, that's not what our definition says. It feels a little bit like that should be what our definition says because of how parts A and B are structured, but that's not what it says. It doesn't say make this integral negative t to t and then take the limit. If it did say that, then this conclusion would be valid. Because on any negative t to t, we have cancellation. The integral negative t to t of this is always going to be 0, and of course the limit of 0 is 0. But that's not what our definition says. It says that we have to look at the two sides separately. So maybe I choose to integrate from 0 to infinity and integrate from minus infinity to 0, x cubed dx. And here we can see this is going to be positive infinity. I'll put this maybe in quotations. And this is going to be like negative infinity. If I try to add these together, I get, again, kind of in quotations, infinity minus infinity. Well, that's an indeterminate form. Often with indeterminate forms, what we see is that, well, being indeterminate means we can't determine what their value is. Sometimes we can do a bit of extra work, like simplify some things or something and figure out what the value is. But at least at first glance, this kind of could be anything. And the idea here is what is so special about choosing this symmetrically? Why couldn't somebody choose to integrate from negative t to 2t, right? And then we get a big positive and a small negative, and this would net to be some big positive number, right? If I integrated from negative t to 2t, what was it, x cubed dx. This is going to be something positive. It's not going to be 0. But if, as I take the limit as t goes to infinity, it's still going to look like integral minus infinity to infinity. I'm just heading to positive infinity at a kind of a different rate than I'm heading to negative infinity. But the limit as t goes to infinity is still going to look the same. Or if I integrate it from negative 2t to positive t, or from, you know, negative, I don't know, t cubed to positive t squared. Why should one of these, namely the integral negative t to t, why should that be preferred over the others? These are all different ways to get the top bound to infinity and the bottom bound to negative infinity. And these are all going to result in different, or many of them are going to result in different claims for what the value of the integral is. Right? This one would seem to suggest a value of 0. This one would suggest a value of plus infinity, or this structure here. This would suggest probably a value of negative infinity. We probably could figure out, it could engineer a solution where we get a value of +1 or something. It seems like that should be the value, or with some careful engineering, we could probably do that. So which one should be preferred? Well, that's why we are careful to break it up this way. Because if I choose to break it at 0 or at -1 or a +5, I'm going to get the same answer no matter what. And each of these, requiring that each of these, that the left-hand side and the right-hand side effectively both separately converge. Kind of practically, one of the benefits of that is it keeps us out of this kind of infinity minus infinity situation where we're getting indeterminate forms. I mean, strictly speaking, this is just the definition and we follow the definition, but why would somebody set the definition this way instead of a different way? Well, because if we set the definition like this, it's quite arbitrary to pick this as the way that we go to minus or plus infinity instead of some other way. We can't say that no matter how we go to minus or plus infinity, we get the same answer. If we could say that, if all of these yielded the same answer all the time, that would be super nice, and then we could say that, but that doesn't work here. So this is why this is a sensible definition. It doesn't have the internal contradictions that might be had with something like that might be had directly, or might be the consequence of something like a definition that did something along these lines. So I'm harping on it a little bit, but again, it's very easy to be just a little bit careless here. Make this integral minus t to t, and then let t go to infinity and argue the answer is 0, when in fact the answer does not exist, or diverges. Okay. So this is in fact, as originally written, a false statement. This integral diverges. Any questions on that? Okay, next example. This is a kind of important and fundamental integral. For what values of p is the following the following integral convergent? Integral 1 to infinity of 1 over x to the p dx. So basically the idea is if p is bigger than 0, so we have kind of some weight of x in the bottom, we're looking at this area, an infinitely long area going off to infinity at the right. And kind of the question is, well, the larger the p is, if I look at 1 over x or 1 over x squared gets bigger faster. So 1 over x squared gets closer to 0 faster. or 1 over x cubed, or 1 over x to the fourth, right? The larger that I make P, my areas, my little chunks of area get smaller faster. It kind of seems like maybe there will be a cutoff P. That if P is at least this big, the areas get small enough, fast enough that I converge. But if P is not bigger than that number, then maybe the areas keep getting smaller and smaller, but they don't quite get small enough, fast enough. Or I can certainly see if P was negative, well, then I have like 1 over, say, for instance, x to the negative 2. Well, that's like x squared, right? Or like y equals x or y equals x cubed or something like that. Uh, so we'd be evaluating this area that gets bigger and bigger as we go off to the right. Of course, those are going to diverge. Okay, so we have 3 cases, or maybe more than 3 cases, but P less than 0 diverges. It's pretty clear, but I will leave it as an exercise to show it carefully. Show it carefully using the definition. What about P equals 0? Well, anything to the 0 is 1. This is just integral 1 to infinity of 1 dx. If we evaluate integral 1 to t of 1 dx, this is dx. This is just t minus 1, which goes to infinity as t goes to infinity. This diverges. So P less than or equal to 0, those don't give me a convergent integral. But again, for P's bigger than 0 is where I think I might have a chance, right? P equals 0 is just the constant function here. So of course, our areas aren't getting, our little chunks of area are not getting smaller as we move to the right. So what about P bigger than 0? This is where we have some promise, right? Where it just feels like it might work. P bigger than 0. So I still do, in a sense, have like a weight of x in the bottom now. So the larger x is, the bigger the bottom gets, the denominator, and the smaller the overall fraction gets. The overall fraction is getting closer and closer to 0. So I am looking now at functions that, as I go to the right, the little chunks of area are getting smaller. But are they getting small enough, fast enough is the real question. Okay, let's take a look. So we're interested in integral 1 to infinity of 1 over x to the p dx. And we need to evaluate integral 1 to the t, or integral from 1 to t of 1 over x to the p dx. And then look at what happens to that as t goes to infinity. Well, I can write this as x to the minus p. I see this is just a power function. I add 1 to the power, divide by the new power, and evaluate from x going, to be clear, this is x going from 1 to t. So this is 1 over 1 minus p times t to the power 1 minus p, subtract, well, 1 to whatever power is just 1. And my question is, what happens to this as t goes to infinity? The 1 over 1 minus p, the minus 1, as an aside, p is bigger than 0, but we have a special case here. What happens if p equals 1? I'm running out of time, so I'm kind of ignoring that here. But what happens if p equals 1? We'll leave that as an exercise as well. If p equals 1, this formula doesn't quite work, right? We have a log floating around, but so we'll look at that as an exercise. But what happens as t goes to infinity? The -1 isn't affected by t changing. The 1/1 minus p isn't affected by t changing, and no problems there so long as p is not equal to 1. So what happens? Well, if t goes to infinity, and if 1 minus p is positive, if 1 minus p is positive, then I have t to a positive power. And as t grows, whether that positive power is 1/2, like a square root, or 1, or 2, like a linear or quadratic, if 1 minus p is positive, this all goes to infinity, we diverge. Or 1 minus p is positive means p is less than 1. So no luck for p less than 0, or p equal to 0, or in fact for p less than 1. On the other hand, if 1 minus p is less than 0, taking 1 minus p equals 0, p equals 1 as a separate case, if 1 minus p is less than 0, then that means that p minus 1 is bigger than 0, or t to the 1 minus p is 1 over t to the p minus 1. So I have 1 over something that's going to infinity. This bit goes to 0. This bit here goes to 0. So what can I say? I can say that this integral equals, well, if this goes to 0, I have negative 1 over 1 minus p. It's 1 over p minus 1. If 1 minus p is less than 0, if p is bigger than 1. It turns out this will diverge as well. So p equals 1 doesn't get us there. That's kind of right on the borderline. The integral 1 over x is the borderline case. So this integral converges if and only if p is bigger than 1, and it converges to the value 1 over p minus 1 in that case. This is an important integral, so in other words, integral 1 to infinity, 1 over x dx diverges. It's an important integral for contradictions, for providing counterexamples. This is an integrand whose areas get small, but they don't get small enough fast enough. So just the areas getting small is not enough for the integral to converge. They have to get small enough fast enough. And in this case, in this situation, that means the power has to be bigger than 1. 1 over x, that doesn't converge, but 1 over x squared, 1 over x cubed, 1 over x to the 3/2 power. In the context of this integral, they would all converge. Those areas get small enough fast enough. Any questions on this? Okay, so I'll probably punt to a supplement, convergence of an improper integral with a discontinuous integrand. If we understand these definitions well and these examples well, as much as this seems like a completely different, completely different type of problem, it's actually much the same. So it's not that big of a jump, not nearly as big as it would seem if we understand the previous material. All right, let me end the recording.